Tonight, we're going to dismantle something you've believed your entire life. You've been told that the universe is made of particles, tiny little balls of matter bouncing around, combining, breaking apart. Electrons, quarks, photons, little objects flying through empty space. That picture is wrong. Not slightly wrong, fundamentally wrong. The deepest layer of reality isn't made of particles at all. It's made of something far stranger, something that fills every cubic centimeter of the universe right now, even the space you're sitting in. They're called quantum fields. And particles, everything you've ever touched, seen, or been made of, are just momentary ripples in those fields. By the end of tonight, you're going to understand what reality actually is. And it's nothing like what you imagined. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already understand, even if you've never thought about it in these terms. Imagine you're standing in a room. Maybe it's your living room, your bedroom, wherever you are right now. The air around you has a temperature. Not just one temperature, but a temperature at every single point in that room. Near the window, it might be cooler. Near the heater, it might be warmer. In the corner near the ceiling, it's probably a bit different than near the floor. If you could somehow measure the temperature at every single point in that room, every cubic centimeter, every cubic millimeter, you'd have what physicists call a field. A temperature field. It's not a physical object. You can't pick it up or hold it in your hand, but it's real. It describes a physical quantity that exists at every point in space. The temperature at one spot might be 68 degrees. A foot to the left, it might be 69. Near the drafty window, it might drop to 63. The temperature field tells you the value of temperature everywhere in the room, all at once, continuously. You don't see it, but it's there. It's a real physical thing that affects everything in the room, from how comfortable you feel to whether a glass of water forms condensation on its surface. Now, a temperature field is a simple example. It assigns a single number to every point in space. Physicists call this a scalar field. Scalar just means it has magnitude but no direction. The temperature at a point is 68 degrees. It doesn't point anywhere, it's just a value. But there are more complex kinds of fields. Think about wind. If you're standing outside on a breezy day, the air isn't just moving. It's moving in a specific direction at every point around you. Near the ground, the wind might be blowing east at 5 miles per hour. 20 feet up, it might be blowing northeast at 12 miles per hour. A wind field doesn't just assign a number to every point in space. It assigns a number and a direction. Physicists call this a vector field. It has both magnitude and direction at every point. These are familiar examples because we experience temperature and wind every day. But the fields that really matter in physics, the ones that underpin the entire universe, are far more fundamental than temperature or wind. And to understand them, we need to go back a few centuries to a time when scientists were grappling with one of the deepest questions in all of physics. How do forces work across empty space? Think about gravity. Right now, Earth is pulling you downward. You feel it constantly. It keeps you in your chair, keeps your feet on the ground, keeps the atmosphere from drifting away into space. But here's the question that puzzled scientists for centuries. How does Earth pull on you? Your feet are touching the ground, sure. But what about the moon? The moon is about 238,000 miles away. And Earth's gravity is pulling on it, keeping it in orbit. How does Earth reach across 238,000 miles of empty space and grab the moon? There's nothing connecting them. No rope, no chain, no physical contact. Just empty vacuum between them. Isaac Newton figured out the mathematics of gravity in 1687. His law of universal gravitation could predict the motion of planets, moons, falling apples, cannonballs, everything. It was spectacularly successful. But even Newton himself was bothered by one aspect of his own theory. It described gravity as action at a distance. Earth just somehow pulls on the moon instantly, across all that empty space, with no physical mechanism to explain how. Newton wrote about this in a famous letter. He said that the idea of one body acting on another through a vacuum, without anything mediating the interaction, was, to him, so great an absurdity that he believed no person who had any competent faculty of thinking could ever fall into it. Newton could calculate gravity with extraordinary precision, but he couldn't explain how it actually worked. He couldn't say what was physically happening between Earth and the moon. He just knew the math gave the right answers. This question, how forces act across empty space, sat unresolved for nearly 2 centuries. The mathematics worked beautifully. Engineers used Newton's equations to predict tides, calculate orbits, and design structures. But the physical mechanism remained a mystery. The force just somehow leaped across the void. Then, in the 1830s and 1840s, a self-taught English scientist named Michael Faraday began to change everything. Faraday wasn't a mathematician. He came from a poor family, had almost no formal education, and worked as a bookbinder's apprentice before getting a job as a laboratory assistant at the Royal Institution in London. But he had an extraordinary physical intuition, an ability to visualize how nature worked, that few scientists before or since have matched. Faraday was studying electricity and magnetism, and he noticed something that troubled him about the way scientists thought about these forces. At the time, the standard picture was similar to Newton's gravity. Electric charges attracted or repelled each other across empty space. Magnets attracted or repelled each other across empty space. No one could explain how. It was just action at a distance, the same mysterious non-explanation that had bothered Newton about gravity. But Faraday saw it differently. When he sprinkled iron filings around a magnet, he saw the filings arrange themselves into beautiful curving lines, extending outward from the magnet's poles. These weren't just pretty patterns. To Faraday, they revealed something physical. The space around the magnet wasn't empty. It was filled with something. The magnet was creating an invisible structure in the space surrounding it. Faraday called these structures lines of force, and he proposed something radical. The force between two magnets wasn't action at a distance. The magnet created something real in the space around it, and this something extended outward in all directions. When another magnet entered that region, it interacted with this invisible structure. It didn't interact directly with the first magnet across empty space. It interacted with the thing the first magnet had created in the space right where the second magnet was sitting. This was a profound shift in thinking. Faraday was saying that the space around a magnet isn't empty. It's filled with a physical entity. The force isn't transmitted from one magnet to the other across a void. The first magnet modifies the space around it, and the second magnet responds to the modified space at its own location. Everything is local. Nothing needs to reach across empty space. The space itself carries the force. most physicists at the time dismissed Faraday's ideas. He couldn't express them mathematically, and in the 1800s, if you couldn't write equations, many scientists wouldn't take you seriously. Faraday's lines of force were seen as a useful visualization tool, not as a description of physical reality. But then came James Clerk Maxwell. Maxwell was a Scottish physicist and one of the greatest mathematical minds of the 19th century. He took Faraday's intuitive pictures and translated them into precise mathematics. Between 1861 and 1865, Maxwell published a set of equations that unified electricity and magnetism into a single framework. These equations, now known as Maxwell's equations, are among the most important in all of physics. And they did something remarkable. They showed that Faraday was right. The space around electric charges and magnets isn't empty. It's filled with electric and magnetic fields. These fields are real physical entities. They carry energy. They carry momentum. They exert forces on charged particles. They're not just mathematical abstractions or convenient visualization tools. They're physically real things that exist in space. But Maxwell's equations revealed something even more astonishing. They predicted that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. This interplay means that once you set up a disturbance in the electromagnetic field, it can propagate on its own, traveling through space as a self-sustaining wave of oscillating electric and magnetic fields. Maxwell calculated the speed of these waves from his equations. The result came out to about 186,000 miles per second. Maxwell immediately recognized this number. It was the speed of light. Light, Maxwell realized, is an electromagnetic wave. It's a ripple in the electromagnetic field traveling through space. This was one of the most stunning unifications in the history of science. Light, which humans have been studying for centuries, which seemed to be its own separate phenomenon, turned out to be a manifestation of the same fields that made magnets attract and electric charges repel. Light is the electromagnetic field in motion. And here's what's crucial for our story tonight. These electromagnetic waves, these ripples in the field, can travel through completely empty space. No medium required. No substance to wave through. The field itself is the thing that's waving. The field fills all of space, and disturbances in it propagate at the speed of light. This means the electromagnetic field exists even in a vacuum, even in empty space where there are no charges, no magnets, no matter at all. The field is always there. It fills the entire universe. If you remove every atom, every particle, every speck of matter from a region of space, the electromagnetic field is still there. It's a fundamental feature of reality, as basic as space itself. Think about what this means. Before Faraday and Maxwell, physicists thought of empty space as truly empty. There was nothing there. Objects could exist in space, forces could act across space, but space itself was just a passive stage where things happened. After Faraday and Maxwell, this picture changed completely. Space isn't empty. It's filled with fields. The electromagnetic field permeates every cubic centimeter of the universe. It's always present, always ready to respond to charges and currents, always capable of carrying waves of light across billions of light years of space. The field is everywhere. Let me be more specific about what a field actually is in physics, because this is important and most explanations either oversimplify it or make it seem more mystical than it is. A field is a physical quantity that has a value at every point in space and time. That's it. That's the definition. At every point in space, right now, the electromagnetic field has a specific value. That value tells you the strength and direction of the electric force and the magnetic force that a charged particle would experience if you placed one at that point. The field exists whether or not there's a particle there to feel it. This is a crucial distinction. The field isn't defined by the particles in it. The field exists independently. Particles respond to the field, and particles can create disturbances in the field, but the field is there regardless. It's like the surface of a lake. The water surface exists whether or not there's a wave on it. You can throw a stone and create a ripple, but the surface was there before the stone hit it. The ripple is something the surface does. The surface itself is the fundamental thing. The ripple is secondary. Now, let me show you why this matters by talking about the gravitational field. Because gravity is the force you experience most directly, and it illustrates the field concept beautifully. When Newton described gravity, he wrote it as a force between two masses. Earth pulls on you. You pull on Earth. The force depends on the masses involved and the distance between them. This description works perfectly for calculations, but it has that troubling feature. It implies the force acts instantaneously across any distance. If the sun suddenly vanished, Newton's theory would say Earth would immediately fly off in a straight line. The gravitational effect would be felt instantly, even though the sun is 93 million miles away. Einstein's general theory of relativity, published in 1915, fixed this problem. And it fixed it by replacing Newton's force with a field. In Einstein's picture, mass doesn't exert a force across empty space. Instead, mass curves space-time itself. The sun's mass warps the fabric of space-time around it, creating a curved geometry. Earth doesn't get pulled by some mysterious invisible force. Earth follows the straightest possible path through curved space-time. The curvature is the field. It exists at every point in space around the sun, and it affects how objects move. If the sun suddenly vanished, the change in the gravitational field wouldn't be felt instantly. It would propagate outward at the speed of light, like a ripple spreading through the field. It would take about 8 minutes and 20 seconds for the change to reach Earth. Nothing travels faster than light, not even changes in the gravitational field. This is the field picture at its most powerful. Forces aren't mysterious actions at a distance. They're mediated by fields that fill space. Changes in those fields propagate at the speed of light. Everything is local. A particle at any point in space responds only to the field at that exact location, not to some distant object it has never been in direct contact with. Here's something that most people find surprising when they first learn about fields. Fields can carry energy and momentum on their own, independently of any particles. When sunlight travels from the sun to Earth, that light is a disturbance in the electromagnetic field. It's a wave, an oscillating pattern of electric and magnetic fields propagating through space. That wave carries energy. When it hits your skin, you feel warmth. When it hits a solar panel, it generates electricity. The energy was carried across 93 million miles of empty space by the field itself. There were no particles carrying it across that distance. The field did it on its own. Electromagnetic waves carry momentum too. This has been confirmed experimentally. Light exerts pressure on surfaces it hits. It's a tiny amount of pressure, far too small to feel, but it's real and measurable. This radiation pressure is what pushes the tails of comets away from the sun. When a comet approaches the sun, solar radiation, which is electromagnetic waves emitted by the sun, pushes gas and dust particles away from the comet. This is why comet tails always point away from the sun, regardless of which direction the comet is moving. The field is doing physical work, it's exerting force, it's transferring energy. And it's doing all of this through empty space with no particles involved in the transmission. Let me give you another example that shows how real fields are. Radio waves. Right now, as you're listening to this, the space around you is filled with radio waves. Signals from radio stations, cell towers, Wi-Fi routers, satellites, television broadcasts, all of them are electromagnetic waves propagating through the electromagnetic field. They pass through you constantly. They pass through walls. They pass through the air. They fill every cubic inch of the room you're in. You don't see them because your eyes are only sensitive to a tiny range of electromagnetic frequencies, the range we call visible light. But radio waves are just as real as visible light. They're the same phenomenon, the same type of disturbance in the electromagnetic field, just at a different frequency. If you turn on a radio, the radio's antenna responds to these electromagnetic waves. It converts the oscillating electromagnetic field into an electrical signal, which then gets converted into sound. The information, the music, the voices, they were carried from the transmitter to your radio entirely by the electromagnetic field. No physical object traveled from the radio station to your radio. The field itself carried the signal. This tells us something profound about the nature of reality. Fields aren't just mathematical tools we invented to make calculations easier. They're physically real entities that fill space, carry energy, exert forces, and transmit information. The electromagnetic field is as real as the chair you're sitting in. You just can't see it directly because human eyes evolved to detect only a narrow range of its behaviors. Now, the electromagnetic field isn't the only field in physics. The gravitational field is another. In Einstein's general relativity, the gravitational field is the curvature of space-time itself. It fills all of space, it carries energy in the form of gravitational waves, and it determines how matter moves. Gravitational waves were first detected directly in 2015 by the LIGO experiment. Two massive black holes, each roughly 30 times the mass of the Sun, spiraled into each other and merged about 1,300,000,000 light years away. The collision sent ripples through the gravitational field, ripples in the fabric of space-time itself. Those ripples traveled across 1,300,000,000 light years of space at the speed of light and reached Earth, where they stretched and compressed space by only a few thousandths of the diameter of a proton. LIGO detected this impossibly tiny distortion. It was one of the most remarkable measurements in the history of science. And what it confirmed was that the gravitational field is real. It can carry waves, just like the electromagnetic field can carry light. These waves carry energy and information across the cosmos. The field is physically real. It does things. So here's where we stand so far. The universe isn't just made of objects floating in empty space. Space itself is filled with fields. The electromagnetic field permeates everything. The gravitational field permeates everything. These fields are always present, always active. They carry energy, they exert forces, they transmit information. They can exist and behave independently of any particles. A beam of light crossing the void between galaxies is the electromagnetic field doing its thing with no particles involved in the transmission across that vast distance. A gravitational wave rippling through space-time is the gravitational field propagating a disturbance, with no matter needed to carry it. The fields are the primary reality. But we're only talking about classical fields right now. Classical fields are fields as Faraday and Maxwell and Einstein understood them. They're smooth, continuous, and can take on any value. The electromagnetic field at a point in space can have any strength. It can vary smoothly from one value to another. There are no jumps, no gaps, no discrete steps. It's like a perfectly smooth surface that can be at any height. This classical picture of fields is incredibly powerful. It explains electromagnetism, gravity, light, radio waves, and much more. But in the early 20th century, physicists discovered something that would shatter this smooth, continuous picture. They discovered that at the smaller scales, fields don't behave smoothly at all. They behave in ways that seemed impossible, ways that contradicted everything classical physics predicted. And this discovery, the discovery that energy comes in discrete chunks rather than continuous streams, would lead to the most successful and most unsettling theory in the history of science. The theory that would eventually reveal what particles really are, why they exist, and what the universe is truly made of at its deepest level. That discovery began with a problem involving light. In the late 1800s, physicists were studying something called black body radiation. A black body is an idealized object that absorbs all electromagnetic radiation that hits it and then re-emits that radiation based on its temperature. A glowing piece of hot metal is a rough approximation of a black body. When you heat metal, it glows. First red, then orange, then yellow, then white as it gets hotter. This glow is electromagnetic radiation, emitted because of the object's temperature. Physicists tried to use classical field theory, specifically Maxwell's electromagnetic theory, to predict how much radiation a black body would emit at each frequency. The prediction was catastrophic. Classical theory said that a hot object should emit infinite amounts of energy at high frequencies. This was clearly wrong. Hot objects don't emit infinite energy. If they did, you'd be vaporized every time you stood near a fire. This failure was called the ultraviolet catastrophe because the theory broke down at the high-frequency ultraviolet end of the spectrum. Classical physics, which works so well for so many things, gave a completely nonsensical answer for something as simple as a glowing hot object. In 1900, the German physicist Max Planck found a mathematical fix. He proposed that electromagnetic energy isn't emitted or absorbed in continuous amounts. Instead, it comes in tiny discrete packets. He called these packets quanta, from the Latin word for how much. Each quantum of electromagnetic energy at a given frequency has an energy equal to a constant, now called Planck's constant, multiplied by the frequency of the radiation. This was a strange assumption. Classical physics said energy should be continuous. You should be able to have any amount of energy, just like you can pour any amount of water into a glass. There's no minimum amount. But Planck was saying no, energy comes in minimum chunks. You can have one quantum, or two quanta, or three, but you can't have 1.5. Energy is granular, not smooth. Planck himself wasn't entirely comfortable with this idea. He initially thought it might be a mathematical trick, a calculating device that happened to give the right answer without reflecting any deeper truth about nature. But the math worked perfectly. Planck's formula for black body radiation matched experimental measurements with extraordinary precision. Something about this strange assumption of discrete energy packets was capturing a real feature of nature. 5 years later, in 1905, Albert Einstein took Planck's idea much further. Einstein proposed that light itself comes in discrete packets, not just the emission and absorption of light, but light itself. Each packet, later called a photon, carries a specific amount of energy determined by the light's frequency. Einstein used this idea to explain the photoelectric effect, a phenomenon where light hitting a metal surface knocks electrons loose. Classical theory couldn't explain the details of this effect, but Einstein's photon model explained it perfectly. And it earned him the Nobel Prize in Physics in 1921. Not for relativity, which is what most people associate with Einstein, but for this discovery about the quantum nature of light. What Planck and Einstein were discovering, though it would take decades to fully understand, was that the electromagnetic field doesn't behave the way classical physics predicted at the smaller scales. The field is quantized. Its energy comes in discrete chunks. These chunks, these quanta of the electromagnetic field, are what we call photons. A photon isn't a little ball of light flying through space, it's a quantum of the electromagnetic field. A discrete packet of energy in the field. The field itself is the fundamental thing. The photon is what you get when the field carries energy in its smallest possible unit at a given frequency. This was the first hint of something revolutionary. Classical fields are smooth and continuous, but real fields, the fields that actually exist in nature, are quantized. They come in discrete steps, and those discrete steps, those quanta, are what we experience as particles. The particle isn't separate from the field. It is the field, vibrating in a specific quantized way. But in 1900 and 1905, nobody fully grasped this yet. The full understanding would take another few decades of work by some of the most brilliant physicists who ever lived. The quantum revolution was just beginning. And as we'll see, it would completely overturn everything scientists thought they knew about what matter is, what particles are, and what reality is made of at its most fundamental level. The smooth, continuous fields of Faraday, Maxwell, and Einstein were about to meet the strange, discrete, probabilistic world of quantum mechanics. And when those two pictures collided, what emerged was something no one expected. A picture of reality where fields are still primary, still fundamental, still filling all of space, but where those fields behave in ways that defy everyday intuition. Ways that produce everything we see, everything we touch, everything we are. That story, how classical fields become quantum fields, and how particles emerge from the quantum nature of those fields, is where we're headed next. And it's gonna change how you think about every physical object you've ever encountered, including yourself. So by the early 1900s, physics had arrived at a crossroads. On one side stood the classical picture of fields, smooth, continuous, elegant. Fields that filled all of space, carried energy, and transmitted forces. Maxwell's electromagnetic field, Einstein's gravitational field. These were triumphs of 19th century physics, beautiful theories that explained everything from the behavior of magnets to the propagation of light across the cosmos. On the other side stood a series of experiments that made no sense within that classical picture. The ultraviolet catastrophe, the photoelectric effect, the spectrum of light emitted by heated atoms. One by one, these experiments were telling physicists something disturbing. The universe doesn't work the way classical physics says it should. Not at the smallest scales. Something else is going on. something fundamentally different. Planck had introduced the idea that energy comes in discrete packets. Einstein had proposed that light itself is made of these packets, photons, but these were patches, fixes applied to specific problems. Nobody yet had a unified picture of what was really happening. Nobody had a framework that could explain why energy was quantized, what this meant for the nature of fields, and how all of this connected to the particles that make up matter. That framework would take another 2 decades to develop. And when it finally came together, it would represent one of the most profound revolutions in the history of human thought. Let's trace how it happened. In 1913, the Danish physicist Niels Bohr proposed a model of the atom that incorporated quantization directly. At the time, physicists knew that atoms consisted of a tiny, dense nucleus surrounded by electrons. But classical physics predicted that electrons orbiting a nucleus should continuously radiate energy and spiral inward, crashing into the nucleus in a tiny fraction of a second. Obviously, this doesn't happen. Atoms are stable. They don't collapse. Bohr's solution was radical. He proposed that electrons in an atom can only occupy specific orbits, specific energy levels. They can't exist at just any distance from the nucleus. They're restricted to certain allowed orbits, like steps on a staircase. An electron can be on the first step or the second step, but it can't be between steps. There's no halfway. When an electron jumps from a higher energy level to a lower one, it emits a photon whose energy equals the difference between the two levels. When it absorbs a photon of exactly the right energy, it jumps up. This explains why atoms emit and absorb light only at specific frequencies, producing the characteristic spectral lines that scientists have been cataloging for decades. Hydrogen, for example, emits light at very specific wavelengths. Red, blue-green, violet. Each color corresponds to an electron jumping between specific energy levels. Bohr's model predicted these wavelengths with remarkable accuracy. But Bohr's model was still a patchwork. It worked well for hydrogen, but struggled with more complex atoms. And it didn't explain why energy levels were quantized in the first place. It was a rule imposed from outside rather than something that emerged naturally from a deeper theory. The deeper theory came in the mid-1920s with the development of quantum mechanics. Between 1925 and 1927, physicists including Werner Heisenberg, Erwin Schrödinger, Max Born, and Paul Dirac constructed a mathematical framework that could describe the behavior of particles at the atomic scale. This framework was strange, deeply counterintuitive, and wildly successful. In quantum mechanics, a particle like an electron isn't described by a definite position and velocity the way a billiard ball would be. Instead, it's described by something called a wave function. The wave function is a mathematical object that encodes all the information about the particle's state. It tells you the probability of finding the particle at each possible location if you measure its position. It tells you the probability of finding it with each possible momentum if you measure its momentum. But here's the key insight. Before you measure, the particle doesn't have a definite position or a definite momentum. It exists in a superposition of possibilities. It's not that we don't know where it is, and it's actually somewhere specific. As far as quantum mechanics is concerned, the particle genuinely doesn't have a definite location until a measurement forces it to take one. This was shocking. In classical physics, objects always have definite properties. A ball is always somewhere. It always has a specific velocity. You might not know these values, but they exist. Quantum mechanics says no. At the fundamental level, certain properties are genuinely indefinite until observed. But quantum mechanics, as developed in the 1920s, had a limitation. It was designed to describe particles: a single electron, a single proton, a single atom. You write down the wave function for the particle, and you calculate how it evolves over time using the Schrödinger equation. This works beautifully for many problems: atomic structure, chemical bonding, the behavior of electrons in metals. But it runs into serious trouble when you try to combine it with Einstein's special theory of relativity. Special relativity, published in 1905, says that space and time are intertwined into a four-dimensional fabric called space-time. It says that nothing can travel faster than light. And crucially for our story, it says that energy and mass are related by the famous equation E equals mc squared. This equation means that energy can be converted into matter and matter into energy. If you have enough energy concentrated in a small enough space, new particles can spontaneously appear, and existing particles can annihilate, converting their mass entirely into energy. This creates a fundamental problem for ordinary quantum mechanics. In the quantum mechanics of the 1920s, the number of particles is fixed. You write down a wave function for 1 electron or 2 electrons or 10 electrons, and you calculate what they do. But you always know how many particles you're dealing with. The number doesn't change. Special relativity says the number of particles can change. Energy can become particles. Particles can become energy. In a high-energy collision, you might start with 2 particles and end up with 20. In a matter-antimatter annihilation, you start with 2 particles and end up with none, just pure energy. Ordinary quantum mechanics can't handle this. It breaks down when you try to describe processes where particles are created or destroyed. This is where quantum field theory enters the picture. And this is where everything we've been building toward comes together. Quantum field theory is what you get when you take the concept of a field, which fills all of space, and apply the rules of quantum mechanics to it. Instead of quantizing particles, you quantize the field itself. And when you do this, something magical happens. Particles emerge automatically. You don't put them in by hand. You don't assume they exist. You start with a field and you apply quantum rules, and particles appear as a natural, inevitable consequence. Let me explain how this works. Start with the electromagnetic field. In classical physics, this field fills all of space. At every point, it has a value for the electric field and a value for the magnetic field. These values can change over time, they can oscillate, and when they oscillate in a coordinated way, you get electromagnetic waves, light. Classical electromagnetic waves can have any energy. You can make a wave as weak as you want or as strong as you want. The energy is continuous. You can dial it up or down smoothly, like a dimmer switch on a light. There are no jumps, no gaps, no minimum amount. Now apply quantum mechanics to this field. Quantize it. What does that mean physically? It means the field can no longer vibrate with any arbitrary amount of energy. Just like Bohr's electron could only occupy certain energy levels in an atom, the electromagnetic field can only carry energy in discrete amounts. The field can have 0 quanta of energy, or 1 quantum, or 2 quanta, or 3, but it can't have 1.5. The energy of the field at any given frequency comes in indivisible packets. Each packet is a quantum of the electromagnetic field. Each packet is what we call a photon. So a photon isn't a tiny ball of light. It's a unit of excitation of the electromagnetic field. When we say there's one photon present, we mean the electromagnetic field at a particular frequency has been excited by exactly one quantum of energy. When we say there are 100 photons, we mean the field has been excited by 100 quanta. The photons don't exist independently of the field. They are the field, carrying energy in discrete quantized units. This is a subtle but incredibly important distinction. In the classical picture, you might imagine photons as little particles flying through the electromagnetic field, like balls rolling across a surface. But that's not what's happening. The photons are excitations of the field itself. They're not things in the field. They're things the field does. The field vibrates, and those vibrations come in discrete energy packets, and each packet is a photon. The field is the fundamental entity. The photon is a consequence of the field's quantum nature. Think of it this way. Imagine a perfectly still lake. The surface of the lake is smooth, flat, undisturbed. Now imagine you disturb the surface. You create a wave. That wave moves across the lake, carrying energy. Now here's the quantum twist. In the quantum version of this lake, you can't create a wave of any size. There's a minimum wave. You can have 1 unit of wave, or 2 units, or 3, but nothing in between. Each unit of wave is a quantum of the lake's surface. The wave isn't something separate from the lake. It is the lake, temporarily disturbed. The lake is always there whether or not waves are present. The waves are just what happen when the lake carries energy. This is exactly how quantum fields work. The electromagnetic field fills all of space, always. It's always there. When it carries energy in discrete packets, those packets are photons. The photons are the field's way of carrying quantized energy. Remove all the photons and the field is still there. It's in its ground state, its lowest energy configuration. But it's not gone. It's never gone. Now here's where this becomes truly revolutionary. The electromagnetic field isn't the only field. It's just one of many. And this is the key insight that transforms our understanding of what matter actually is. Every type of particle in the universe corresponds to its own quantum field. There is an electron field that fills all of space. There is an up quark field that fills all of space. There is a down quark field, a muon field, a tau field, a neutrino field for each flavor of neutrino, and on and on. Each of these fields permeates every point in the universe, right now, at this very moment. The space around you isn't just filled with the electromagnetic field, it's filled with dozens of quantum fields, all overlapping, all coexisting, all occupying the same space simultaneously. An electron isn't a little ball of matter sitting in space. An electron is a quantum of excitation of the electron field. Just as a photon is a quantum of the electromagnetic field, an electron is a quantum of the electron field. The electron field fills all of space, and when it's excited by one quantum of energy in a localized region, that excitation is what we observe as an electron. Let this sink in for a moment because it's a radical departure from how most people think about matter. You probably grew up imagining electrons as tiny spheres orbiting the nucleus of an atom, like planets orbiting the sun. That picture is wrong. An electron isn't a tiny sphere. It isn't an object at all, not in the way you normally think of objects. It's an excitation of a field, a ripple in the electron field, a quantized disturbance in an invisible entity that fills the entire universe. The same is true for quarks, the particles that make up protons and neutrons. There's an up quark field and a down quark field, both filling all of space. Protons and neutrons are made of quarks, which means protons and neutrons are ultimately patterns of excitations in the quark fields. And since atoms are made of protons, neutrons, and electrons, atoms themselves are patterns of excitations in various quantum fields. Everything you see around you, every object, every person, every star, every galaxy, is made of excitations in quantum fields. The chair you're sitting in is a collection of about 10 to the power of 28 atoms, each one a complex arrangement of excitations in the electron field, the up quark field, the down quark field, and the fields that mediate the forces holding everything together. Your own body is the same. You are a pattern of excitations in quantum fields. Not particles in the traditional sense, excitations, vibrations, ripples in fields that fill the entire universe. Now, not all quantum fields are the same. They come in two broad categories, and the difference between these categories has enormous consequences for how the universe works. The two categories are called boson fields and fermion fields. Boson fields are the fields whose excitations are force-carrying particles. The electromagnetic field is a boson field. Its excitations, photons, are bosons. There are other boson fields too. The fields that carry the strong nuclear force, whose excitations are gluons. The fields that carry the weak nuclear force, whose excitations are the W and Z bosons. And there's the gravitational field, whose hypothetical quanta would be gravitons, though we haven't detected individual gravitons yet. Fermion fields are the fields whose excitations are matter particles. The electron field, the quark fields, the neutrino fields, these are all fermion fields. Their excitations, electrons, quarks, neutrinos, are fermions. Fermions are what make up the matter you interact with every day. There's a fundamental difference in how bosons and fermions behave, and it comes down to a property that has no classical equivalent. Bosons are social. Multiple bosons can occupy the same quantum state at the same time. You can pile as many photons into the same state as you want. This is what makes lasers possible. In a laser, billions of photons occupy the exact same quantum state, all vibrating in perfect synchrony. Bosons don't mind being in the same state. They actually prefer it. This is called Bose-Einstein statistics, named after Satyendra Nath Bose and Albert Einstein. Fermions are the opposite. They're exclusive. No two fermions of the same type can occupy the same quantum state at the same time. This is the Pauli exclusion principle, discovered by Wolfgang Pauli in 1925. It's one of the most important principles in all of physics because it's the reason atoms have structure. Without the Pauli exclusion principle, all the electrons in an atom would collapse into the lowest energy state. There would be no electron shells, no chemical properties, no periodic table, no chemistry, no molecules, no life. The exclusion principle forces electrons to fill up energy levels one by one, giving each element its unique chemical behavior. It's the reason you have a body. It's the reason matter is solid. It's the reason you don't fall through the floor. So the universe is filled with two kinds of quantum fields: boson fields that carry forces and fermion fields that make up matter. All of them fill all of space. All of them are quantized. And the particles we observe, every photon, every electron, every quark, every neutrino, are excitations of these fields. Not independent objects that happen to be described by field theory. Actual excitations, ripples, quanta. The fields come first. The particles are a consequence. There's one more field I need to mention, and it's a special one. A field that doesn't quite fit neatly into either category because it does something none of the other fields do. It gives mass to particles. I'm talking about the field associated with the mechanism that explains why some particles have mass and others don't. This field fills all of space like every other quantum field, but unlike the electromagnetic field, which has zero value on average in empty space, this particular field has a non-zero value everywhere. Even in a perfect vacuum, even in the emptiest part of the universe, this field is always on. It always has a value, and particles that interact with this field acquire mass because of that interaction. Particles that don't interact with it, like the photon, remain massless. The more strongly a particle interacts with this field, the more massive it becomes. The quantum of this field, the excitation you get when you disturb it, was detected at CERN in 2012. Its discovery confirmed that this field exists, and that it permeates all of space exactly as the theory predicted. The discovery was one of the most important confirmations in the history of particle physics. Now, let me address something that's crucial for understanding quantum fields, because it's one of the most misunderstood concepts in all of science. The vacuum, empty space. What happens when you remove every particle from a region? What's left? In classical physics, the answer is simple: nothing. If you remove every atom, every photon, every speck of matter and energy from a region of space, you're left with true emptiness, a void, nothing at all. In quantum field theory, the answer is profoundly different. If you remove every particle from a region of space, you haven't removed the fields. The fields are still there, all of them. The electromagnetic field, the electron field, the quark fields, the neutrino fields, all of them remain. They're in their ground states, their lowest possible energy configurations. No excitations are present, which means no particles are present. But the fields themselves are still there, filling every point in that region of space. And here's what makes this genuinely strange. Even in their ground states, quantum fields aren't perfectly still. They can't be. This is a direct consequence of one of the most fundamental principles in quantum mechanics, the uncertainty principle. Heisenberg's uncertainty principle says you can't simultaneously know both the exact value of a field and the exact rate at which that value is changing. If the field were perfectly still, you'd know both. The value would be zero, and the rate of change would be zero. But quantum mechanics forbids this. So even in the ground state, the field fluctuates. Tiny random vibrations occur constantly, everywhere, in every quantum field. These are called vacuum fluctuations. And they're not mathematical fictions. They have real, measurable physical effects. One of the most famous is the Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948, and confirmed experimentally in 1997. If you place two uncharged metal plates very close together in a vacuum, the vacuum fluctuations of the electromagnetic field between the plates are slightly different from those outside the plates. The result is a tiny but measurable force pushing the plates together. Two metal plates in empty space, with nothing between them but the quantum vacuum, experience a real physical force caused by the quantum fluctuations of a field in its ground state. The vacuum isn't empty, it's seething with activity. The fields are there, and they're fluctuating, even when no particles are present. Vacuum fluctuations also affect the properties of particles in measurable ways. The most famous example is the Lamb shift, measured by Willis Lamb in 1947. The Lamb shift is a tiny difference in energy between two energy levels in the hydrogen atom that should be identical according to basic quantum mechanics. The difference arises because the electron in the hydrogen atom interacts with the vacuum fluctuations of the electromagnetic field. The constantly flickering quantum vacuum slightly shifts the electron's energy, and this shift is measurable with high precision. The theoretical prediction of the Lamb shift from quantum field theory matches the experimental measurement to about 6 significant figures. That's like predicting the distance from New York to Los Angeles to within a few steps. It was one of the earliest and most convincing confirmations that quantum field theory was capturing something real about nature, something that no previous theory had been able to explain. This precision tells us something important. Quantum field theory isn't just a nice idea or a useful approximation. It's an extraordinarily accurate description of how reality actually works. The fields are real. Their vacuum fluctuations are real. The particles they produce are real. And the mathematical framework that describes all of this, quantum field theory, has been tested to a degree of precision that no other scientific theory in history has matched. So let me summarize what we've established so far, because this is the foundation for everything that comes next. The universe is filled with quantum fields. Not one field, but many. Each type of particle corresponds to a specific field. The electromagnetic field, the electron field, the quark fields, the neutrino fields, and others. All of these fields permeate every point in space, all the time. They overlap. They coexist. They're always present. Particles are not independent objects floating in these fields. Particles are quantized excitations of the fields. A photon is a quantum of the electromagnetic field. An electron is a quantum of the electron field. A quark is a quantum of the quark field. The fields are the fundamental entities. The particles are derived from them. Even in empty space, the fields are present. They're in their ground states with no particles present, but they're not still. They fluctuate constantly due to the quantum uncertainty principle. These fluctuations have real, measurable effects that have been confirmed experimentally to extraordinary precision. The fields come in two types. Boson fields, whose excitations carry forces, and fermion fields, whose excitations constitute matter. The fundamental difference between bosons and fermions, that bosons can share quantum states while fermions cannot, is responsible for the structure of atoms, the solidity of matter, and ultimately the existence of chemistry and life. This is the picture that modern physics gives us. Not a universe of tiny balls bouncing around in empty space, but a universe of fields, invisible, space-filling, quantum fields, whose excitations create everything we see and everything we are. The fields are the deeper reality. The particles are the surface, the manifestation, the observable consequence of something far more fundamental happening underneath. And this picture, strange as it seems, is the most precisely tested and experimentally confirmed description of nature that humans have ever produced. But we've only scratched the surface. Because understanding that particles are excitations of fields raises profound questions. What does it really mean for a particle to be an excitation? What happens when two excitations interact? Why are all electrons identical? And what does this tell us about the ultimate nature of matter itself? Those questions are going to take us even deeper into the quantum world, and the answers are going to be even more surprising than what we've seen so far. Because once you truly understand what it means for a particle to be a ripple in a field, your entire picture of what matter is, what objects are, what you yourself are changes completely. So we've established that particles are excitations of quantum fields. But what does that actually mean? What is an excitation? When physicists say an electron is an excitation of the electron field, what are they describing physically? Because if we're going to claim that everything you've ever touched, everything you've ever seen, everything you are is made of field excitations rather than little solid objects, we need to understand what an excitation really is. And to do that, let's start with something you can actually picture. Imagine a guitar string. The string is stretched tight between two fixed points. When nothing is happening, the string is still. It sits there at rest, not vibrating, not producing any sound. This is the string's ground state, its lowest energy configuration. Now pluck the string. You've added energy to it. The string starts to vibrate. It oscillates back and forth, producing a sound wave. That vibration is an excitation of the string. It's not a separate thing that was added to the string. It is the string, behaving differently because energy was added. The vibration doesn't exist independently. You can't remove the vibration and hold it in your hand. You can't separate it from the string. The vibration is something the string does. It's a pattern of motion in the string itself, and the vibration carries energy. When the string vibrates, it pushes air molecules, creating sound waves. The energy you put in when you pluck the string is being carried by the vibration and transmitted to the surrounding air. The string is the fundamental thing. The vibration is what happens when you add energy to it. Now here's an important detail. A guitar string can't vibrate at just any frequency. It has specific modes of vibration, specific patterns that are allowed by the physics of the string. The lowest frequency mode is the fundamental. The string vibrates in a single smooth arc. Then there are harmonics, higher frequency modes where the string vibrates in 2 arcs, 3 arcs, 4 arcs, and so on. These modes are determined by the length, tension, and thickness of the string. They're discrete. The string can vibrate at the fundamental frequency, or at twice that frequency, or 3 times, but not at 1.5 times. The allowed modes are quantized. A quantum field is similar in some ways, but far more complex. The field fills all of space, not just the length between 2 fixed points. And it can vibrate, meaning its value at different points can oscillate. When the field vibrates in a specific quantized way, that vibration is a particle. The particle is to the quantum field what the vibration is to the guitar string. It's not a separate thing, it's the field doing something. The field, excited by a specific amount of energy in a specific pattern, produces what we observe as a particle. The field is the fundamental entity. The particle is the excitation. But here's where the guitar string analogy starts to mislead, and it's important to understand where it breaks down. A guitar string vibration is spread out along the entire string. It's not localized at one point. A particle, on the other hand, often appears to be localized. When you detect an electron, you detect it at a specific location. It hits a detector at a particular point. It leaves a track in a particle detector. It seems to be somewhere. How can something that's an excitation of a field filling all of space appear to be at a specific location? The answer is that quantum field excitations can be localized. Think about a different analogy. Instead of a guitar string, imagine the surface of a calm ocean. The ocean stretches in every direction as far as you can see. It's essentially infinite from your perspective. Now imagine you drop a stone into the water. A ripple forms. It's localized near where the stone hit. It's not everywhere at once. It's concentrated in a specific region. Over time, the ripple might spread out, but initially it's localized. That ripple is an excitation of the ocean's surface. It's not a separate object placed on the ocean. It is the ocean, temporarily disturbed in a localized region. The ocean is the fundamental thing. The ripple is something the ocean does at a particular location. A particle in a quantum field is something like this. It's a localized disturbance, a concentrated bundle of energy in the field. When you detect an electron at a specific location, you're detecting a localized excitation of the electron field. The field is everywhere, filling all of space. But the excitation, the extra energy, the disturbance is concentrated in a small region. That concentrated region is where we say the electron is. But unlike a water ripple, which is a classical wave that can have any amount of energy, a quantum field excitation is quantized. The electron field can't be excited by just any amount of energy. The minimum excitation, the smallest possible disturbance that constitutes a particle, corresponds to a specific quantum of energy. That quantum is 1 electron. You can have 1 electron, or 2 electrons, or 1,000 electrons, but you can't have half an electron. The excitation is quantized. It comes in discrete, indivisible units. Now, there's a subtlety here that often gets lost in popular explanations. The particle isn't just a lump of energy sitting in the field like a pebble resting on a blanket. It's more dynamic than that. The excitation is constantly interacting with the field, with other fields, with the vacuum fluctuations we discussed earlier. The particle is a dynamic process, not a static object. It's more like a whirlpool in a river than a rock on a road. A whirlpool is a recognizable pattern. It has a location, a size, a certain behavior, but it's made of water that's constantly flowing through it. The whirlpool is a process, a persistent pattern in a flowing medium. If you could somehow tag individual water molecules, you'd see them entering the whirlpool, swirling around, and leaving. The molecules change. The pattern persists. A particle is something like this. It's a persistent, quantized pattern in a quantum field. The field is always active, always fluctuating. The particle is a stable excitation within that dynamic field, a pattern that maintains its identity even as the underlying field constantly shifts and fluctuates. This brings us to one of the most profound implications of quantum field theory: creation and annihilation. In a particle picture where particles are little objects, it's very hard to explain how particles can be created or destroyed. Where does a new particle come from? Where does a destroyed particle go? If particles are fundamental objects, the irreducible building blocks of reality, then creating or destroying them seems almost magical. Something comes from nothing, or something vanishes into nothing. But in the field picture, creation and annihilation are completely natural. They're not mysterious at all. When a particle is created, what's actually happening is that a quantum field is gaining an excitation. The field was in one state, and now it's in a higher energy state with one more quantum of excitation. The particle didn't come from nowhere. The field was always there. It just got excited. Think back to the ocean analogy. When a wave forms on the ocean, the wave didn't come from somewhere else. The ocean was already there. Energy was added, and the ocean responded by producing a wave. The wave was created, but nothing was created from nothing. The ocean gained a disturbance. That's all. Similarly, when a particle is destroyed, when it annihilates, the field simply loses an excitation. It drops from a higher energy state to a lower one. The particle didn't go somewhere. The field just returned to a less excited state. The field is still there. It's always there. It just has one fewer quantum of excitation now. This is why matter-antimatter annihilation makes sense in quantum field theory. When an electron meets a positron, which is the electron's antimatter counterpart, they annihilate. Both particles disappear, and in their place, photons are produced. In the particle picture, this seems bizarre. Two objects just vanish and are replaced by completely different objects. But in the field picture, it's straightforward. The electron field had one excitation, the electron, and one anti-excitation, the positron. When they meet, the excitation and the anti-excitation cancel out. The electron field returns to its ground state. But the energy that was in those excitations doesn't disappear. Energy is always conserved. That energy goes into exciting the electromagnetic field, creating photons. One field loses excitations. Another field gains excitations. The total energy is conserved. Nothing mysterious is happening. It's just energy being transferred between fields. This process is happening constantly throughout the universe. In the cores of stars, nuclear reactions create and destroy particles. Protons fuse together. In the process, some quarks change type, neutrinos are emitted, and photons are produced. All of this is fields exchanging excitations. One field loses a quantum, another field gains a quantum. Energy flows from one field to another. The particles we observe are just the bookkeeping. The fields are doing the real work. Let's talk about what happens at particle accelerators like CERN, because this is where the field picture becomes most vivid. At the Large Hadron Collider, protons are accelerated to nearly the speed of light and then smashed together. The collisions produce enormous amounts of energy concentrated in a tiny region of space. What happens in those collisions isn't really protons bouncing off each other like billiard balls. What's happening is that the quantum fields in that tiny region are being excited to incredibly high energy levels. And when you pump that much energy into quantum fields, all sorts of excitations can appear. Think about it this way. You start with two protons, which are excitations of quark and gluon fields. You slam them together, concentrating enormous energy in a microscopic volume. That energy excites every quantum field in that region. The electron field gets excited, producing electrons and positrons. The muon field gets excited, producing muons and antimuons. The quark fields get excited at higher energy levels, producing heavier quarks. Fields corresponding to heavier, rarer particles get excited too. All of these excitations are the particles that the detectors at CERN observe. The critical point is that the new particles that appear weren't hiding inside the protons. They weren't little Russian dolls nested within each other. The proton didn't contain an electron waiting to pop out. What happened is that the energy from the collision excited different quantum fields, and those fields produced new excitations, new particles. The particles were created from the energy of the collision through the excitation of quantum fields. The fields were always there. They were always filling that space. They were just in their ground states, unexcited. The collision provided enough energy to kick them into excited states, producing particles that hadn't existed a moment before. This is how the famous discovery at CERN in 2012 worked. The field associated with the mechanism that gives other particles mass had never been excited in a laboratory. Its quanta had never been directly observed. But physicists knew the field had to exist, because without it, the mathematics of particle physics fell apart. So they built the Large Hadron Collider, accelerated protons to within a fraction of a percent of the speed of light, and smashed them together with enough energy to excite this field. The excitation appeared as a new particle in the detector. The field had been there all along, filling all of space, never observed directly because no one had ever concentrated enough energy to excite it. The particle itself exists for only a tiny fraction of a second before decaying into other particles, other field excitations, but its brief appearance confirmed that the underlying field is real. Now let's explore something that strikes at the very heart of what it means to be a thing. Consider electrons. Every atom in your body contains electrons. Your body contains roughly 7 times 10 to the power of 27 electrons. That's a 7 followed by 27 zeros. Each one of these electrons is, as far as we can tell, absolutely identical to every other electron in the universe. Not just similar, not just really close, identical, the same mass, down to as many decimal places as we can measure. The same electric charge, exactly. The same spin, exactly. The same magnetic moment, exactly. Every electron that has ever been measured has the same properties as every other electron. There has never been a single exception. In the particle picture, this is a stunning coincidence that demands explanation. If electrons are independent little objects, why are they all exactly the same? When you manufacture objects in a factory, they're similar but never exactly identical. There are always tiny variations. No 2 baseballs are exactly the same weight. No 2 coins are exactly the same size. So why are electrons all precisely, exactly, perfectly identical? In the field picture, the answer is obvious. All electrons are excitations of the same field. There is one electron field filling the entire universe. When that field is excited by one quantum of energy in one location, you get an electron here. When it's excited by one quantum of energy in another location, you get an electron there. But both excitations are excitations of the same field. They have to have the same properties because they're the same type of disturbance in the same underlying entity. Think about water waves again. If you create 2 identical waves on the same lake, they have the same properties because they're both waves in the same water. The water determines what kinds of waves are possible. The properties of the wave, its speed, its behavior, are determined by the properties of the water. 2 waves in the same water will naturally have the same characteristics. This is why all electrons are identical. They're not independent objects that happen to be the same. They're excitations of a single field, and the properties of that field determine the properties of every excitation. There's only one electron field, so there's only one set of possible electron properties. This has a breathtaking implication. Every electron in the universe is fundamentally the same entity expressing itself in different locations. The electron in a hydrogen atom on Earth and the electron in a hydrogen atom in a galaxy 10 billion light years away are both excitations of the same electron field. They're connected, not through any mysterious force, but because they're ripples in the same underlying substance. The electron field doesn't stop at the edge of Earth's atmosphere, or at the edge of the solar system, or at the edge of the Milky Way. It extends across the entire universe, continuous and unbroken, and every electron everywhere is a quantum of that one field. The physicist Richard Feynman's thesis advisor, John Archibald Wheeler, once suggested a playful idea along these lines. He proposed that maybe there is only one electron in the entire universe, zigzagging forward and backward in time, appearing simultaneously at every point where an electron is needed. This idea, while not taken literally in modern physics, captures something true about the field picture. There isn't a separate electron for every location. There's one electron field, and what we call individual electrons are just localized excitations of that single field. Now let's talk about something that makes the quantum field picture even more strange and even more compelling: virtual particles. We discussed vacuum fluctuations earlier, the fact that even in empty space, quantum fields can't be perfectly still. They fluctuate constantly, their values jittering up and down due to the uncertainty principle. These fluctuations can briefly create what physicists call virtual particles. A virtual particle is an excitation of a quantum field that appears and disappears too quickly to be directly observed as a real particle. It borrows energy from the vacuum, as allowed by the uncertainty principle, exists for an incredibly brief time, and then vanishes. The uncertainty principle says that the shorter the time an energy fluctuation lasts, the larger the energy fluctuation can be. So for extremely brief moments, the vacuum can produce excitations with significant energy. These virtual particles pop in and out of existence constantly, everywhere in space, all the time. Now, virtual particles are a tricky concept, and there's debate among physicists about how literally to interpret them. In the mathematics of quantum field theory, virtual particles appear as intermediate steps in calculations. When you calculate the probability of one particle interacting with another, the calculation involves summing over all possible intermediate states, including states where additional particles briefly exist. These intermediate particles are the virtual particles. They're not directly observed, you can't catch one in a detector, but their effects are measurable. The Lamb shift that I mentioned earlier, where the energy levels of hydrogen are slightly shifted from what basic theory predicts, is caused by virtual particles. The electron in the hydrogen atom interacts with virtual photons and virtual electron-positron pairs that briefly appear from vacuum fluctuations of the electromagnetic and electron fields. These interactions shift the electron's energy by a tiny but measurable amount. The theoretical prediction, which includes the effects of virtual particles, matches the experimental measurement to extraordinary precision. The anomalous magnetic moment of the electron is another example. The magnetic moment of an electron, which describes how it behaves in a magnetic field, is slightly different from what basic quantum mechanics predicts. The difference is caused by the electron interacting with virtual particles in the quantum vacuum. The predicted value of the electron's magnetic moment, calculated including virtual particle effects, agrees with the measured value to astonishing precision. And it depends critically on virtual particles, on the idea that the quantum fields are constantly fluctuating, and that these fluctuations have real physical consequences. What virtual particles tell us is that the quantum vacuum is not passive. It's not just a quiet backdrop against which particles play out their dramas. It's an active participant. The fields are always fluctuating, always producing brief excitations, always affecting the particles that exist within them. Every real particle in the universe is constantly interacting with the quantum vacuum, constantly exchanging virtual particles with the fluctuating fields. This interaction affects the particle's properties, its mass, its charge, its magnetic moment. No particle exists in isolation. Every particle is embedded in a seething quantum vacuum that shapes its behavior. Let me give you a specific example to make this concrete. Consider two electrons sitting near each other. They repel each other because they both have negative electric charge. In the old picture, they just push each other away through some mysterious force acting at a distance. In the field picture, the repulsion happens through the electromagnetic field. One electron creates a disturbance in the electromagnetic field. That disturbance propagates through the field and reaches the other electron, pushing it away. The disturbance is carried by virtual photons, quantum fluctuations in the electromagnetic field that mediate the force between the two charged particles. In Feynman's famous diagrams, which are graphical representations of these calculations, you draw two electron lines coming in and a wavy line representing a virtual photon being exchanged between them. The virtual photon carries momentum from one electron to the other, which is what creates the repulsive force. The photon is virtual because it's never directly observed. It exists only as an intermediate step in the interaction, but its effects are completely real. The repulsion between two electrons is real. The force is real. And that force is mediated by the quantum fluctuations of the electromagnetic field. Every force you've ever experienced works this way. The electric force that holds atoms together is mediated by virtual photons exchanged between charged particles through the electromagnetic field. The strong nuclear force that holds protons and neutrons together in atomic nuclei is mediated by virtual gluons exchanged through the gluon fields. The weak nuclear force responsible for certain types of radioactive decay is mediated by virtual W and Z bosons exchanged through their respective fields. And gravity, though we don't yet have a complete quantum theory of it, is thought to be mediated by virtual gravitons exchanged through the gravitational field. Forces aren't mysterious pushes and pulls acting through empty space. They're the result of quantum fields constantly exchanging excitations. The fields are the medium through which all forces operate. Without the fields, there would be no forces. Without forces, there would be no atoms, no molecules, no stars, no planets, no you. Let me paint you a picture of what reality looks like according to quantum field theory, because it's nothing like what your intuition suggests. Imagine you could somehow see quantum fields directly. You'd see them filling all of space, overlapping, interpenetrating, each one present everywhere at once. The electromagnetic field, the electron field, the quark fields, the gluon fields, the neutrino fields, all of them occupying the same space, simultaneously. And they wouldn't be still. They'd be shimmering, fluctuating constantly. Even in empty space, the fields would be alive with activity, their values jittering up and down, virtual excitations appearing and vanishing in a constant fizz of quantum activity. In regions where matter exists, you'd see stable excitations, persistent patterns in the fields that maintain their identity over time. An electron would appear as a concentrated ripple in the electron field, a localized bundle of energy that moves through space. A proton would appear as a complex pattern of excitations in the quark and gluon fields. 3 quark excitations bound together by a seething cloud of virtual gluon excitations. An atom would appear as an intricate dance of excitations across multiple fields. Electron field excitations orbiting a core of quark and gluon field excitations. All of them constantly exchanging virtual excitations with each other and with the fluctuating vacuum around them. Nothing would look solid. Nothing would look like a little ball or a tiny object. Everything would be waves, ripples, vibrations in fields, concentrated in some places, spread out in others, constantly in motion, constantly interacting. The sharp, well-defined objects of our everyday experience, Tables, chairs, rocks, people would reveal themselves as incredibly complex patterns of field excitations. Stable patterns, to be sure, patterns that maintain their structure for years or decades or centuries, but patterns nonetheless. Not things, processes. You are not made of things. You are made of processes. Persistent, stable, self-maintaining patterns in quantum fields. The atoms in your body are arrangements of field excitations. The molecules are larger arrangements. The cells are larger still. Your body is an enormously complex pattern of excitations in multiple quantum fields, a pattern that maintains itself by constantly exchanging energy and particles with its environment. You eat food, which is a different arrangement of field excitations. Your body disassembles those excitations and reassembles them into its own pattern. You breathe in oxygen molecules, excitations of the electron and quark fields arranged in a particular way. And you breathe out carbon dioxide, the same types of field excitations arranged differently. You are a persistent pattern in quantum fields, constantly exchanging material with your environment, constantly rebuilding yourself, never quite the same from one moment to the next, but always maintaining the overall pattern that is you. This is what quantum field theory tells us about the nature of matter, about the nature of reality, about the nature of you. There are no tiny solid balls at the bottom of everything. There are no irreducible little objects that matter is made of. There are fields, quantum fields, filling all of space, fluctuating constantly, and the particles and atoms and molecules and objects and people that we see are all patterns of excitations in those fields. The fields are the reality. Everything else is what the fields do. And perhaps the most remarkable thing about all of this is that it works. Quantum field theory isn't philosophy or speculation. It's a precise mathematical framework that makes predictions. Predictions that have been confirmed by experiment to extraordinary precision. The magnetic moment of the electron, the Lamb shift, the spectrum of hydrogen, the cross-sections of particle collisions at CERN, the properties of every particle in the Standard Model. All of these have been calculated using quantum field theory and confirmed by experiment. The agreement between theory and experiment is often better than 1 part in a billion. There is no other theory in the history of science that has been tested this thoroughly and confirmed this precisely. Quantum field theory is, by any measure, the most successful scientific theory humans have ever produced. And what it tells us is that the universe is made of fields, not particles, not little objects. Fields, invisible, space-filling quantum fields, whose excitations produce everything that exists. That's a hard truth to absorb. It goes against every instinct we have about the world. When you pick up a rock, it feels solid, heavy, real. It doesn't feel like a pattern of excitations in quantum fields. When you look at the stars, they look like points of light, not distant regions where fields are excited to extraordinary energy levels. Our senses evolved to help us survive in a world of medium-sized objects at human-accessible speeds and temperatures. They didn't evolve to perceive quantum fields. So the field picture feels abstract, alien, disconnected from everyday experience, but it's real. It's the most accurate description of nature we've ever discovered. And when you understand it, when you truly absorb what it means, it changes how you see everything. Every object you encounter, every person you talk to, every star. You look at it in the night sky, all of it is quantum fields doing what quantum fields do. Vibrating, fluctuating, exchanging excitations, creating the astonishing complexity of the physical world from a surprisingly simple set of underlying rules. And we haven't yet reached the deepest implication of all. Because if particles are secondary, if they're just excitations of more fundamental fields, then what does this mean for how we understand reality itself? What does it mean for the Standard Model, for the structure of physics, for our picture of what the universe is made of at the most basic level? Those questions are where we're going next, and the answers will take us to the very bottom of what modern physics has to say about the nature of existence. So now we arrive at the deepest question of all. If particles are just excitations of quantum fields, if the fields are what's truly fundamental, then why does modern physics treat fields as more real than particles? Why can't we just stick with the particle picture that served us well for centuries? What breaks if we insist that particles are the bottom layer of reality? The answer isn't philosophical. It's practical, mathematical, and experimentally forced. The particle picture doesn't just become inconvenient at a certain point. It actually fails. It gives wrong answers. It can't describe what we observe. And the places where it fails reveal exactly why fields must be more fundamental. Let's start with something I touched on earlier but didn't fully explain. The number of particles in a system is not fixed. This is one of the most important facts about quantum field theory, and one of the clearest reasons why a particle-first picture of the universe cannot work. In ordinary quantum mechanics, the kind developed in the 1920s, you start with a fixed number of particles. You might have 1 electron, or 2 electrons, or 50. You write down a wave function for that specific number of particles, and you calculate how the system evolves. The number never changes. If you start with 2 electrons, you always have 2 electrons. The math simply doesn't allow particles to appear or disappear. But nature does allow this. Experiments prove it conclusively. In radioactive beta decay, a neutron inside an atomic nucleus transforms into a proton. In the process, an electron and an anti-neutrino are created. They didn't exist before the decay. There was a neutron, and then there was a proton, an electron, and an anti-neutrino. The number of particles changed. In pair production, a high-energy photon passing near an atomic nucleus can spontaneously transform into an electron and a positron. 1 particle becomes 2. The photon disappears and 2 new particles appear in its place. In matter-antimatter annihilation, an electron and a positron collide and both disappear. In their place, 2 or more photons are produced. 2 particles become different particles entirely. The original particles are gone. None of this can be described by ordinary quantum mechanics with a fixed number of particles. The math simply doesn't have room for it. You can't describe a process where the number of things changes if your framework starts by assuming the number of things is constant. This is not a small problem. It's a fundamental limitation. And it's the reason physicists had to develop quantum field theory. In quantum field theory, the number of particles isn't fixed, because particles aren't fundamental objects. They're excitations of fields, and the number of excitations can change. A field can gain an excitation, which we observe as a particle being created. A field can lose an excitation, which we observe as a particle being destroyed. One field can transfer energy to another field, which we observe as one type of particle transforming into another type. All of this happens naturally and consistently within the mathematical framework. There's no mystery, no special mechanism needed. Particle creation and destruction are just changes in the excitation levels of quantum fields. This resolves one of the deepest puzzles in physics. Where do new particles come from during high-energy collisions? In a particle-only picture, you'd have to imagine particles being pulled out of thin air, materializing from nothing, which seems to violate basic principles of conservation. But in the field picture, no particles are created from nothing. The fields were already there. They were always there, filling all of space. The collision provided energy, and that energy excited the fields. The new particles are new excitations. Nothing was created from nothing. Energy was transferred to fields that were already present, and those fields responded by producing quanta. Now here's another fundamental reason why fields must be more basic than particles. It has to do with the relationship between quantum mechanics and special relativity. This is deep, and most popular explanations skip over it, but it's crucial for understanding why physicists believe what they believe. Special relativity says that space and time are unified into space-time. Events that happen at the same time in one reference frame might happen at different times in another reference frame, moving relative to the first. This is called the relativity of simultaneity, and it's one of the most counterintuitive but well-confirmed predictions of Einstein's theory. Now, consider what this means for particles. Suppose you have a detector and you observe a particle being created at a specific point in space and time. In your reference frame, the particle appears at a definite moment, but an observer moving relative to you might disagree about when the particle was created. They might even disagree about the ordering of events. In some cases, if two events are separated by a space-like interval, different observers can disagree about which happened first. This creates an immediate problem for a particle-first picture. If particles are the fundamental objects, then the question of how many particles exist at a given moment should have a definite answer. But relativity says that the answer to what exists at a given moment depends on your reference frame. Different observers in different states of motion can disagree about how many particles exist at a particular time. This is not acceptable for a fundamental theory. The basic entities of reality can't depend on who's looking. The number of fundamental things can't change depending on your velocity. But the number of particles can change depending on your reference frame. This was demonstrated dramatically by a phenomenon known as the Unruh effect, predicted theoretically by William Unruh in 1976. The Unruh effect says that an observer accelerating through empty space will detect particles, will see the vacuum as being filled with a warm bath of particles, even though an observer at rest in the same region of space detects nothing at all. The accelerating observer sees particles where the stationary observer sees empty vacuum. The two observers disagree about whether particles are present. If particles were the fundamental entities, this would be a paradox. How can one observer see particles and another see nothing? But if fields are fundamental, there's no paradox at all. Both observers agree about the state of the quantum fields. They just disagree about how to decompose that field state into particles. The field is the objective reality. The particles are frame-dependent interpretations of that reality. This is one of the most powerful arguments for the primacy of fields over particles. Fields are the same for all observers. Particles are not. A similar phenomenon occurs near black holes. In 1974, Stephen Hawking showed theoretically that black holes aren't perfectly black. They emit radiation, now called Hawking radiation. The intense curvature of space-time near a black hole's event horizon affects quantum fields in such a way that excitations are produced. An observer far from the black hole detects a faint glow of particles being emitted. But an observer falling freely through the event horizon detects nothing unusual. Again, two observers disagree about whether particles are present. The fields are the same objective reality for both observers, but the particle content of those fields, the number and type of excitations, depends on the observer's state of motion and their relationship to the curved spacetime. These examples show something profound. Particles are not observer-independent. The number and type of particles present in a region of space can depend on who is doing the observing, on their state of motion, on whether they're accelerating, on the geometry of space-time around them. This means particles cannot be the fundamental description of reality. A fundamental description must be the same for all observers. Quantum fields satisfy this criterion. The quantum state of the fields is observer-independent. What changes between observers is how they interpret that state in terms of particles. The fields are the bedrock. The particles are the interpretation. Now, let me explain how the standard model of particle physics fits into this picture, because this is where the field first view becomes most concrete and most powerful. The standard model is the theory that describes all known fundamental forces except gravity. It describes electromagnetism, the strong nuclear force, and the weak nuclear force. It catalogues all known fundamental particles, and despite its name, the standard model is not really a model of particles, it's a model of fields. The standard model contains 17 fundamental fields, not 17 fundamental particles, 17 fundamental fields. The particles that we observe are the excitations of those fields. Let me list them so you can see the full picture. There are 6 quark fields: the up quark field, the down quark field, the charm quark field, the strange quark field, the top quark field, and the bottom quark field. Each one fills all of space. Each one's excitations are the corresponding quarks. Then, there are 6 lepton fields: the electron field, the muon field, the tau field, and 3 neutrino fields, one for each charged lepton. Again, each fills all of space, and each one's excitations are the corresponding particles. Then, there are the force-carrying boson fields, the electromagnetic field, whose excitations are photons, the weak force fields, whose excitations are the W and Z bosons, and the gluon field, whose 8 types of excitations carry the strong nuclear force. Finally, there's the field responsible for giving mass to other particles, whose excitation was discovered at CERN in 2012. That's it. 17 fields. These 17 quantum fields, plus gravity, which the standard model doesn't fully incorporate, are all you need to describe everything we've ever observed in the physical world. Every atom, every molecule, every chemical reaction, every ray of light, every nuclear reaction, every star, every galaxy, everything is a consequence of these 17 fields and their interactions. When particle physicists talk about discovering a new particle, what they really mean is that they found evidence for a new field. The particle they detect is the excitation. But the truly important thing is the field, because the field exists everywhere, all the time. The particle only exists when the field is excited. The field is permanent. The particle is temporary. The field is universal, filling all of space. The particle is local, existing only where the field happens to be excited. The interactions between particles, which is to say the forces that govern how matter behaves, are really interactions between fields. When an electron and a proton attract each other electromagnetically, what's actually happening is that the electron field and the electromagnetic field and the quark fields inside the proton are all interacting with each other. The excitation in the electron field creates a disturbance in the electromagnetic field. That disturbance propagates through space and affects the excitations in the quark fields that make up the proton. This exchange of disturbances is what we experience as the electromagnetic force. The fields talk to each other. They exchange energy. They influence each other's excitations. And all of this happens through well-defined mathematical rules that quantum field theory specifies precisely. The precision of these predictions is worth pausing on because it tells us how seriously we should take this framework. The anomalous magnetic moment of the electron has been measured experimentally to extraordinary precision. The theoretical prediction from quantum field theory agrees with this measurement to about 10 significant figures, roughly 1 part in 10 billion. No other prediction in all of science, in any field, in any discipline, has been confirmed to this level of accuracy. It stands as the most precise agreement between theory and observation ever achieved by humanity. And it comes from quantum field theory, from treating fields as the fundamental entities and calculating how their excitations behave and interact. The strong nuclear force provides another dramatic confirmation. Quantum chromodynamics, the quantum field theory of the strong force, predicts that quarks can never be found in isolation. They're always confined inside composite particles like protons and neutrons. This prediction, called confinement, emerges naturally from the properties of the gluon fields. Gluons, the excitations of the strong force fields, carry the strong charge themselves, unlike photons which are electrically neutral. This means gluon fields interact with each other, creating a situation where the force between quarks doesn't weaken with distance the way electromagnetism does. Instead, it stays constant or even grows stronger. If you try to pull a quark away from its partners, you have to add more and more energy. Eventually, you add so much energy that it's sufficient to excite the quark fields and create a new quark-antiquark pair. The original quark remains bound. You can never isolate it. This has been confirmed by decades of experiments at particle accelerators around the world. No isolated quark has ever been observed. The prediction of confinement comes directly from the properties of the quantum fields, not from any assumption about particles themselves. Now, let me address a question that thoughtful people often ask at this point. If fields are the fundamental reality, why do we experience a world of particles and objects? Why doesn't the field nature of reality manifest in our everyday experience? Why do things look and feel solid rather than looking like shimmering fields of excitations? The answer has to do with scale and energy. At the energy scales of everyday life, field excitations behave in ways that are very well approximated by the particle picture. When an electron is bound in an atom, it behaves as though it's a discrete little thing occupying certain energy levels. When a photon hits a detector, it triggers a localized event, a single click, a single spot on a photographic plate. At these everyday energy scales, the quantum field picture and the particle picture give essentially the same predictions. The fields are there. They're doing the real work. But their behavior at these scales is well captured by treating excitations as particles. It's only when you push to extreme conditions, very high energies, very strong gravitational fields, very precise measurements, that the differences between the field picture and the particle picture become apparent. At CERN, where protons collide at energies equivalent to trillions of degrees, the field nature of reality becomes impossible to ignore. Particles are created and destroyed freely. The number of particles changes from moment to moment. Different types of particles transform into each other. All of this is natural in the field picture and impossible in a particle-only picture. Near black holes, where space-time curvature is extreme, the observer dependence of particles becomes important. In the early universe, when temperatures were unimaginably high, the quantum fields were in dramatically different states than they are today. And understanding those states requires the full machinery of quantum field theory. So our everyday experience of a world of solid objects and definite particles is an approximation. An incredibly good approximation for the conditions we normally encounter, but an approximation nonetheless. The deeper reality is fields, always fields, and when conditions become extreme enough, the deeper reality shows through. There's another profound implication of the field picture that deserves attention. It concerns the nature of empty space itself. We've discussed vacuum fluctuations, the fact that quantum fields fluctuate even in their ground states. But there's something even deeper going on. The vacuum state of the universe, the state where all fields are in their lowest energy configuration, is not just alive with fluctuations. It actually has a structure. It has energy. And this vacuum energy has cosmological consequences. When physicists calculate the total energy of the vacuum, adding up the contributions from the ground state fluctuations of all quantum fields, they get a number. A very large number. In fact, the naive calculation gives a vacuum energy that's enormous, roughly 120 orders of magnitude larger than what we observe cosmologically. This discrepancy, the largest disagreement between theory and observation in the history of physics, is called the cosmological constant problem. It's one of the deepest unsolved problems in theoretical physics. What we do observe is that the vacuum has a small but non-zero energy. This vacuum energy is what drives the accelerating expansion of the universe. It's what cosmologists call dark energy. The expansion of the universe is accelerating because the quantum vacuum itself has energy, and that energy pushes space apart. So the quantum fields that fill all of space, even in their ground states, even when no particles are present, have enough energy to drive the expansion of the entire cosmos. The vacuum isn't empty. It is physical properties that affect the fate of the universe itself. This connection between the quantum vacuum and the large-scale fate of the cosmos is one of the most remarkable links in all of physics. The same quantum fields that produce electrons and photons and quarks at the subatomic scale also contribute to the vacuum energy that determines whether the universe expands forever or eventually collapses. The very small and the very large are connected through the quantum fields that underpin everything. Now, let me be honest about what we don't know, because quantum field theory, for all its success, is not the final word. There are deep questions it cannot answer. The biggest is gravity. The Standard Model describes 3 of the 4 known forces: electromagnetism, the strong force, and the weak force. All 3 are described by quantum field theories that work beautifully. But gravity resists quantization. When physicists try to construct a quantum field theory of gravity, treating the gravitational field the same way they treat the electromagnetic field, the mathematics breaks down. The calculations produce infinities that can't be removed by the standard techniques. This doesn't mean that gravity isn't a quantum field. It almost certainly is, at some level. But the quantum field theory framework, as we currently understand it, isn't powerful enough to describe quantum gravity. Something more is needed. String theory is one attempt to go beyond quantum field theory. It proposes that the fundamental entities aren't zero-dimensional point particles or their associated fields, but one-dimensional vibrating strings. Different vibrational modes of these strings correspond to different particles. In a sense, string theory replaces quantum fields with something even deeper. But string theory has its own problems. It requires extra spatial dimensions beyond the three we observe. It comes in multiple versions that are hard to distinguish experimentally. And despite decades of work, it has not yet made a prediction that can be tested with current or near-future technology. Loop quantum gravity is another approach. It tries to quantize gravity directly by quantizing space-time itself, replacing the smooth, continuous fabric of space-time with a discrete structure at the smaller scales. In loop quantum gravity, space is made of tiny, discrete units, something like atoms of space. This approach doesn't require extra dimensions, but it has its own unresolved technical problems. The truth is, we don't yet know what lies beneath quantum field theory. We know quantum field theory is extraordinarily successful. We know it correctly describes everything we've ever observed at the subatomic level. But we also know it's incomplete because it can't incorporate gravity. Whatever replaces or extends quantum field theory will have to reproduce all of its successes while also describing quantum gravity. It will almost certainly be even stranger than quantum field theory itself, and it will probably reveal that quantum fields, fundamental as they seem to us now, are themselves manifestations of something even deeper. But let's step back from the frontiers of theoretical physics and consider what all of this means, what it really means for how we understand the world and our place in it. Because the shift from a particle picture to a field picture isn't just a technical detail, it's a profound change in our understanding of what reality is. For centuries, the intuitive picture of the universe was atomistic. Reality was made of things, little objects, fundamental building blocks, irreducible pieces of matter. The ancient Greeks imagined atoms, indivisible particles that combined in different ways to form everything we see. Modern physics initially seemed to confirm this picture. We discovered atoms, then we discovered that atoms are made of protons, neutrons, and electrons. We discovered that protons and neutrons are made of quarks. At each stage, we found smaller things inside bigger things, like opening Russian dolls. Quantum field theory breaks this chain. At the bottom, there are no things. There are no little objects. There are no irreducible building blocks in the traditional sense. At the bottom, there are fields. Invisible, intangible, space-filling quantum fields. And everything we see, everything we experience, every object and every organism and every star and every galaxy is a pattern of excitations in those fields. The solid, tangible world we experience is built from something that is neither solid nor tangible. It's built from vibrations in fields that we can't see, can't touch, can't directly perceive. Yet those fields are more real, more fundamental, more permanent than anything we can see or touch. The chair you're sitting in will eventually break apart. The atoms in it will scatter. The particles will eventually be absorbed or transformed. But the fields, the electron field, the quark fields, the electromagnetic field, those will still be there. They'll still fill all of space. They were there before the chair existed, and they'll be there long after it's gone. The particles come and go. The fields remain. There's something humbling and beautiful about this picture. You are a temporary pattern in eternal fields. The atoms in your body were forged in stars, nuclear reactions that shuffled excitations between quantum fields. Those atoms came together to form you, a pattern so complex that it became aware of itself. And someday, those atoms will disperse. The excitations that make up your body will return to the fields, the energy redistributed, the pattern dissolved, but the fields will remain. The substrate from which you arose will still be there, filling all of space, still capable of producing new excitations, new patterns, new complexity. When you look up at the night sky and see the stars, you're seeing the electromagnetic field in action. Photons, excitations of that field that have traveled for years or centuries or millennia to reach your eyes. Each photon is a quantum of the electromagnetic field, created when the field was excited in a distant star and absorbed when it excites the electron fields in the molecules of your retina. The field connects you to those distant stars. The same field that permeates the space around you also permeates the space around every star in every galaxy. It's one continuous entity spanning the entire universe, and every atom in your body is connected to every other atom in the universe through the quantum fields that make up both. The electron field in your body is the same electron field that exists in a nebula 10,000 light years away. The quark fields in your atoms are the same quark fields that exist in the core of a neutron star in another galaxy. These fields are universal, unbroken, continuous across the entire cosmos. You are literally physically connected to the entire universe through the quantum fields that make up everything. This is what a quantum field really is. It's the fundamental substance of reality. Not matter, not energy, not particles. Fields. Invisible entities that fill all of space, vibrating in quantized patterns that produce everything we see and everything we are. The particles we observe, the electrons, the quarks, the photons, the neutrinos, are not the deepest layer. They are excitations, ripples, momentary expressions of something more permanent and more fundamental. The universe is not made of things. It's made of fields. And you, sitting here right now, listening to these words, thinking about what they mean, you are a pattern of excitations in those fields. A pattern so intricate, so complex, so extraordinary that it became conscious. A pattern that can contemplate its own existence, understand the fields it's made of, and wonder at the nature of the reality that produced it. Every single thing you have ever seen, touched, heard, tasted, or felt is a quantum field doing what quantum fields do. The warmth of sunlight is the electromagnetic field transferring energy to the electron fields in your skin. The sound of music is pressure waves in air, themselves driven by electromagnetic forces between atoms, which are all excitations of quantum fields. The taste of food is chemical reactions between molecules, all governed by the interactions of quantum fields. Your thoughts, your memories, your emotions, all of them emerge from the electrochemical activity of neurons, which are made of atoms, which are made of field excitations. Everything traces back to the fields. Everything. This is the picture that emerges from over a century of careful experiment and profound theoretical insight. It's the most accurate, most precisely confirmed description of nature that humans have ever achieved. And its central message is clear. The world isn't what it seems. Beneath the apparent solidity, beneath the apparent separateness of objects, Beneath the appearance of distinct particles making up distinct things, there is something deeper, something unified, something that fills all of space and connects everything to everything else. Quantum fields, the true fabric of reality. The next time you hold a rock in your hand and feel its weight, remember what you're actually holding. You're holding a pattern of excitations in quantum fields. Fields that stretch across the entire universe. Fields that have existed since the earliest moments after the Big Bang. Fields that will still be there long after the rock has crumbled to dust and the dust has scattered to the void. The rock feels solid and permanent and real. And it is real. But what makes it real isn't the particles inside it. It's the fields. It's always been the fields. Thank you for joining me on this journey into the deepest layer of reality that modern physics has uncovered. If you found this exploration valuable, a like or subscribe would mean the world. It helps me keep making these deep dives into the mysteries of the cosmos. And remember, the next time you look at anything at all, you're looking at quantum fields in action. The universe isn't made of stuff. It's made of vibrations in invisible fields that fill all of creation. And those vibrations, those fleeting patterns in eternal fields, are everything that exists, including you. Sleep well tonight, knowing that you are made of the same fields that fill every corner of the universe. You are not separate from the cosmos. You are the cosmos, temporarily organized into a pattern that can wonder at its own existence. Good night.